Hello, everyone. So we're starting our Neuro-Symbolic semester today. Alex is going to be busy for the next 2 weeks. So today it's going to be Rodrigo and I moderating this event. So thanks, Rodrigo, for helping with this. And we are having Adam today with us. So thank you very much, Adam, for joining us today. So, Adam, at first, I'll share a few slides with general logistics and news while everyone is joining, and I'll pass it over to you in a few minutes. Okay, let me make it full screen. I want to see what this slow today. Okay. I hope you can see my screen now, right? Okay, I cannot see or hear anyone because I'm in the presentation mode, but I hope it's visible. So as usually, these are the ways that you can join us via Discord, GitHub. You can watch us on YouTube, on LinkedIn, or check our learning site, or you can participate in our communities. You can also work with us. So if you're interested, we have weekly informal, our internal meetings, plus some working meetings. And if you're interested in joining, please email Alex. And here are some topics of interest for us. So if you're specializing in any of those and you're interested to collaborate with us, please email Alex. Neuro-Symbolic Agentic protocol, you have heard about it already, but if you're interested, please go to GitHub and check all the details. Bring your own project. Okay, this is a new thing. So if you have a Neuro-Symbolic AI project, we can host it if you're interested. Benefits for you is visibility and engagement with the community. And also, if we really like your project, it may even result in a tutorial in our upcoming summer school this August. And by the way, it's August 6th and 7th. I'll announce it soon. Again, here is the list of classical papers that we are planning to present someday. If anyone is interested in presenting any of those, please reach out to us. And there are some other ways to get involved. We are hiring. Again, you can email Alex. And we are helping Neuro-Symbolic AI startups with visibility. You can email at our info mailbox. And also, if you are interested in donating or volunteering, here is a couple of links. And again, you can email Alex. This is just a reminder, our 1 hour format. We are going to have 60 minutes today, about 30 to 40 minutes for presentation, and 15 to 20 minutes for Q&A. And if there are some questions left after this, then other questions may be answered on our Discord channel. Okay, here is again information about our upcoming summer school. It's going to happen in August 6th and 7th. You can sign up using this link. And we are actively working on it, working on big names, tutorials, presentations, startup talks. So agenda is coming. So if you're interested in this event, in the news, we are going to share the news so you can sign up using this link. Okay, and today we have Adam with us. Adam will speak about deep arguing. Very interesting. Sounds very interesting. Adam is a PhD student at Imperial College London. He is specializing in artificial intelligence and machine learning. Here is the link for his paper covered today, as we shared on Discord as well. A couple of his sites, if you're interested to connect with Adam. Maybe, I'm not sure, Adam, if you're interested in collaborating or anything, but anyway, here are the sites. And as always, comments or questions welcome in our free channels, Discord, YouTube, and LinkedIn. We are going to check all of those. And next time in a week, we are going to have Sunny Willinger presenting interpretable hybrid machine learning models. And that's it from my end. Now I can pass it over to Adam for your presentation. Adam.
Thank you so much. And thank you so much for inviting me. Can you see my slides okay? Great, perfect. Yeah, so thank you for that introduction. Yeah, today I'm going to be talking about my work on deep arguing, which was supervised by Francesca Toni as well. So as I'm sure we all know, deep learning is the field of machine learning that focuses on deep neural networks. And deep neural networks are incredibly beneficial. They have a high capacity, which means they're capable of learning many different concepts and encoding those within their parameters. And additionally, as we add more and more parameters, typically the amount of concepts that these neural networks can learn increases. So these models are really scalable. And we've seen things like large language models, as they get larger and larger, they're capable of doing more and more tasks. Additionally, deep neural networks work across different modalities. So they work for images, tabular data sets. You can also do multi-modality models. However, a lot of the drawbacks come with using deep neural networks, such as the fact that when you have thousands or even millions of parameters, it becomes impossible for humans to figure out what each of those parameters is doing. And it's even more difficult given the fact that some parameters might even do one or two jobs at the same time or represent more than one concept at the same time. Additionally, actually trying to understand what features are extracted from the data becomes incredibly difficult. Oftentimes, features might be quite fuzzy. They're not aligned necessarily with human concepts. And it's even more difficult when there's no explicit reasoning mechanism in the neural network. So even if we did know what features the network was using, we still don't know what the neural network is doing with those features. So to address those concerns, we introduced deep arguing. So this is a novel neurosymbolic approach for interpretable classification. And the idea behind deep arguing is to use deep neural networks to create argumentation structures that we can actually reason over with using formal argumentation semantics. And I'll explain what that means in a moment. We're going to show how, by using differentiable operations for both construction of the argumentation graph and also with these semantics, we can actually train deep arguing end to end. So that means that our neural networks can actually learn how to do feature extraction at the same time as doing explicit reasoning. And I'm going to show how we can use things like fuzzy logic or optimization objectives to enforce constraints on our argumentation graph structure for the benefit of better interpretability. But to begin with, I'm going to just talk a little bit about the background on computational argumentation. So computational argumentation is a field of machine learning that focuses on a few main things. One, how to model arguments. So an argument can be sort of any representation that we want to use in a debate. For example, it could be natural language. Someone could say, deep learning models are easy to understand. Someone else might say, deep learning models may have too many variables to interpret. And someone else could say, humans cannot simultaneously reason about millions of interacting variables. So each of these are individual arguments. And we don't just want to be able to model arguments, but we also want to model how these arguments interact. So in argumentation, there's almost always an attacks relationship. For example, the fact that deep learning models may have too many variables to interpret attacks the fact that deep learning models are easy to understand. And in this work, we also use a supports relationship. So the fact that humans cannot simultaneously reason about millions of interacting variables supports the fact that deep learning models may have too many variables to interpret. Now, Just being able to model arguments and their interactions isn't enough. We also want to be able to use argumentation to determine which arguments hold and which arguments do not. So we want to compute acceptability. There are lots of different ways to compute which arguments are acceptable or not. And the different types of methods is called an argumentation semantics. So here we might say, well, these arguments are unattacked. So we want to accept the fact that humans cannot simultaneously reason about millions of variables, and that deep learning models may have too many variables to interpret. And therefore, we reject that deep learning models are easy to understand. If only proving this was actually that simple. Now, it's important to note that arguments in computational argumentation don't have to be natural language. And in fact, in the work with deep arguing, they're not natural language arguments. Arguments could be images, they could be logical rules, they could be legal regulations, any sort of representation that you want to argue about. For the moment, I'm going to just represent them using these abstracts A, B, and C. Now, in our work, we use a type of computational argumentation called a quantitative bipolar argumentation framework. Quantitative just means that instead of having arguments that we accept or reject, we're going to score arguments, for example, from 0 to 1. Bipolar just means that we have attacks and supports as well. So in a quantitative bipolar argumentation framework, or a QBAF, we start off each argument with a base score. So this is an intrinsic strength of the argument between 0 and 1. I like to think about this as how strongly we might agree with an argument, regardless of how it interacts with any other argument. So because it's scoring between 0 and 1, A might have a base score of 0.5, which means we're not that confident about whether argument A should hold or not. We might be slightly more confident, in fact, that B doesn't hold because it's got a score of 0.4, and more confident that C does hold with a score of 0.7. We can also assign weights to each of these edges. So we might assign a negative weight, say negative 0.8 to attacks, and a positive weight, say this weight has 0.5 to supports. And then given that we have now our kind of initial prior on what we think about arguments' acceptability and the way in which arguments interact, we can compute our semantics as a degree of final strength, again scored between 0 and 1. So for this argument C, because it's not attacked or supported, we would expect that its final strength to be 0.7. So actually this argument, it's quite near 1, so we might consider that actually we should accept this argument. Because B is supported and not attacked, we would expect that its final strength to increase compared to its base score. And in fact, here, if we compute the semantics, we might say get a score of 0.75. So its acceptability has increased given the fact that it's supported. And now, because A is attacked by an argument which has a fairly strong score, we would expect that its final acceptability to decrease. So in this case, it decreases to 0. Now, the specific algorithm we use for computing the semantics, it's a bit mathematical, so I'm not going to go into it in this presentation. But if you want to read the details about that, you can read that in my paper. So deep arguing is a new method that we've introduced where we're going to use a QBAF to actually make classifications about data points. So in this QBAF, each of our arguments is actually going to be some data point from our training data. But we start off with what we call target arguments. So target arguments are what are our topics of the debate. So because we're doing classification, we want to argue about whether a data point is in, say, class 0 or class 1. In this case, class 0 is going to represent things that are cars, and class 1 is going to represent things that are planes. And what we're going to do is, using representative samples from our training data, we're going to use those as evidence for why an argument should be in class 0 or in class 1. So each of these images that we can see are from the CIFAR10 dataset. We're going to refer to them as cases because they're what we're using as our evidence, and the whole set of cases as our case space. Now, arguments will attack any cases which have a different label to them and support any cases which have the same label to them. So as we can see, there are only supports between arguments that are cars, and there are only attacks between the cars and the planes. And we'll get on to how we determine what should be attacking or supporting what in a moment. Now, when we've got a new case that we want to classify, first what we do is we add that to our QBAF by having it attack any arguments that are irrelevant to it. So the way I like to think about this is we're identifying which pieces of evidence don't matter for the case that we're trying to classify. So here, for example, the red car doesn't matter to our new case, and also the fighter jet doesn't matter to it. Then what happens is the rest of the arguments will debate through our argumentation semantics that I demonstrated before, and will compute an acceptability for each of these arguments. Now, in this case, the target argument for class 0 would have the greatest acceptability compared to the target argument for class 1. And so therefore, we would predict that this new case is actually a car. So we can see how the model works at a high level, but what we want to know is how do we actually construct the QBAF? And the way we do that is using deep neural networks. So because we're using a quantitative bipolar argumentation framework, each of the arguments is associated with a base score and an edge weight. So we can use a deep neural network architecture to actually learn what those base scores are and what the edge weights should be. So the way this works is we take each data point and we pass it through some feature extractor. So for the CIFAR10 dataset, for example, that might be a ResNet. And then we can take that feature representation in the latent space. And for the base scores, we can pass that to a feed-forward neural network to output what the base score is directly. For the edge weights, what we do is we take a pair of feature representations, and we again pass those to a neural network. But then we take the resulting embeddings from those neural networks and we pass it to a function that compares the result and outputs edge weights. So essentially, the deep neural networks are learning how to argue with the data that we provide it. So to show that a bit more graphically, if we look at the red car on the right, what we do is pass that through our shared feature extractor to get some latent space embedding. We pass that into a feed-forward neural network, which will output a base score for the red car. We would do the exact same thing for all of the arguments. So if we looked at this plane, for example, we again pass that through the same feature extractor as before to get an embedding, and we would again pass that through the base score function to get a base score for that argument. For the edge weights, what we do is a little bit different. We take the feature embeddings from both of the images, and we pass those through another neural network. And again, these would be the same neural network to output a new feature embedding that we can then use a function that will compare these embeddings and output the final weight for this edge between the car and the plane. And we do this for all pairs of arguments in order to output edges for the entire graph. Now, I said that the case space, so the set of data points that we're arguing as our evidence, is a set of representative samples. So we need some way to decide what those representative samples are. In the past, I worked on a method called gradual ACBR, where instead of using representative samples, I use the entire training data as the case space. The issue with that is that approach doesn't scale particularly well. especially when you get onto data sets with thousands or even millions of data points. And so in this work, we looked at using k-means clustering, where what we did was we clustered the data set where we had k clusters for each of the classes. So before we looked at, I think there were 3 clusters for the planes and 3 clusters for the cars, for example. And then to make sure that we're not just using the cluster center, which might be a bit too fuzzy because it would be the average of all of the data points in the cluster. What we do is we take the data points that are nearest the cluster center, and those are the ones that we add to our k-space. Now, we can train deep arguing. We can train it end to end. And the reason we're able to do that is because both the graph construction and the argumentation semantics are differentiable operations. This means that we can use a slight variation on a standard gradient descent algorithm combined with backpropagation to actually train our neural networks. The main difference between standard gradient descent and the variant that we use in deep arguing is that we include a fit step. So the fit step is where we actually construct our QBAF. So to just go through that step by step, we would have our forward pass as normal. But first, we construct the QBAF using our k-space, as well as the new case that we're making a prediction for. Then we compute the prediction by applying the argumentation semantics. So this is where we would then compute which target argument has the greatest acceptability. Then we compute the loss function. So we want to minimize the classification error, as well as any optimization objectives that improve the model interpretability, which we'll talk about on the next slide. And then we can update the parameters using backpropagation through the compute graph, just as we would when we're training a standard neural network. Now, in practice, when we implement this in the code, we use batching. So we can actually, instead of updating the structure of the argumentation graph for each new case that we're making a prediction for, we can use one structure, pass in a whole bunch of new cases, do the forward pass, and then do one backwards pass with the average of the gradients, which leads to much more efficient training. Now, for the loss function, as I mentioned, we want to minimize a classification error. So we use a cross-entropy loss function. Now, it's important to note that we use cross-entropy loss function even if we're doing binary classification. And this is because we always have one target argument for each output class. If we did something like with neural networks, where we just had one output node and we use binary cross-entropy, that would be an issue because we have to associate each output node with a class. And if we just picked one class arbitrarily, we might end up biasing the model towards one class. And so we instead just use cross-entropy. We also have a loss term called L delta. This ensures that the target arguments are always the topics of the debate. So essentially, what we want is that the target argument should never attack or support any other arguments, because they're the things that we want to be arguing about. And also, we want to always ensure that each of the target arguments is at least attacked or supported once, because if they're not attacked or supported at all, it means we can never make predictions for those classes. I'm not going to get into the mathematical implementation of these loss functions, but again, if you're interested, you can check out our deep arguing paper. We have another loss term that optimizes the graph structure so that way it doesn't contain any cycles. The reason we want an acyclic graph is because one, if the graph contains cycles, it might be quite difficult for us to interpret. You might imagine two people who are arguing on Reddit or Twitter, and they keep just repeating the same arguments over and over, just kind of yelling at each other. We want to avoid those types of interactions in our argument graphs. And the second reason is that if we have cycles, when we compute our semantics, what we might find is that semantics doesn't converge to a final solution. So this is because we have a graph structure, we compute the semantics iteratively. And if there are cycles, what we might find is that one iteration, we're predicting class 0, the next iteration, we're predicting class 1, then class 0 again, then class 1, and so on and so forth, and we never make a final decision. Whereas if the graph is completely acyclic, then it's guaranteed to converge to one class. The other thing that we want to do is make sure that the graph is sparse. So we enforce this condition both on the interactions between our representative samples in our case space, as well as with the attacks from our new case that are doing the identifying which cases are irrelevant. And the reason we want sparsity is because we want to try and make the predictions using as small a graph as possible. This makes it easier for us to parse. It also, I found, generalizes better and leads to better performance for the most part. Now, we have one other condition that we want to enforce on the graph. And this one we don't enforce by construction, but this one we don't enforce by optimization, but instead we enforce when we're constructing the graph. And that's a minimality constraint. When I said earlier that we have a function for comparing embeddings of two different data points in order to output their edge weight, it's there that we will enforce this minimality condition. What this condition does is if we have two arguments that are quite similar, it might be redundant for them to both support or both attack the same argument. So if we looked at our example before with our cars and our planes, but we just focus on the red car and the orange car, what we have here is that the orange car is supporting the target argument for class 0. So we could also add that the red car should support the target argument for class 0. But given that the red car already supports the orange car, it would be a bit redundant to have an extra support from the red car to the target argument for that class. And similarly, the same thing applies for the attacks. So it'd be a bit redundant for the red car to attack the target argument for class 1, given that the orange car is already doing it and the red car is supporting that attack. And this actually plays out across all of our case space. And so there are quite a few different interactions that we might see beyond just what I'm visualizing here. So as I mentioned, we encode this into the comparison function. But the way we enforce this is by using some logical constraints. Now, specifically, we want to use a fuzzy logical constraint. So for those who aren't familiar, typically in logic, we might have a statement like R equals P and Q, where P, Q, and R are all true and false. So in this statement, it means that R can only be true if both P and Q are both true. And if either P or Q is false, then R would be false. In fuzzy logic, we do something similar, but rather than using true or false, we use values between 0 and 1, where 0 would mean false and 1 would mean true. So we use a type of fuzzy logic called Gould fuzzy logic. That's where we can enforce that the AND logical operation is represented by the minimum function. There are a few different types of fuzzy logics, but I found that for this work, the Gould fuzzy logic seemed to generalize better. I'm not going to get into details of exactly how we encode the constraint in the logic. The function's a little bit complicated. And again, you can read our paper if you're interested. But really, the important thing to note is that we can use this fuzzy logic to enforce this minimality constraint. And by using fuzzy logic, it means that argumentation construction remains differentiable, and so we can do our end-to-end learning. Okay, so now we know what the method is. The question is, well, does it actually work? So we ran a few experiments looking at some tabular data sets as well as some imaging data sets. And we selected these data sets because they range from a few hundred instances all the way up to thousands of instances, or even in the case of Higgs, a few million instances. They're both binary classification tasks as well as multi-class classification, so all the way up to 18 classes in the case of the chess dataset. They're fairly high dimensional for the most part, the tabular datasets and also the imaging datasets. Now, when we constructed the deep arguing models, we used different feature extractors depending on what the dataset was that we were using. So for the tabular datasets, all of the feature extractors were feed-forward neural networks. For the MNIST and fashion MNIST datasets, we used convolutional neural networks. And for CIFAR10, we used a pre-trained ResNet. We compared our approach against a few baselines. One was just against deep neural networks directly, so no argumentation. And the architecture that we used for the deep neural network would have been similar to the architecture that we used for deep arguing. So it would be the same feature extractor, and then typically some linear layer or feed-forward neural network at the end to make a final classification directly. And then, as I mentioned, gradual ACBR earlier, this was a previous approach that I developed, which is similar to deep arguing, but it could only really use small one-layer neural networks, really. And so it didn't scale particularly well. And we'll actually see how that affects the results in a moment as well. And finally, we also compared against decision trees, just to act as a simple symbolic interpretable baseline. What we found in our results overall is that our approach performed quite comparatively to the deep neural networks. The performance trade-off was only really around 1 or 2% for the most part, and actually seemed to perform better on the imaging data sets. So really what we found is that generally there's not a performance trade-off when using deep arguing, despite the fact that we get the extra interpretability from the argumentation. And then for the gradual ACBR model, what we found is that it ran out of memory pretty much every dataset that we tried. And again, this was because, as I mentioned, it didn't use any form of case-based selection. And so a lot of the times the models just ran out of memory when we were trying to train them. And then for the one data set where it didn't run out of memory, because there were much fewer instances, what we found is that actually it didn't end up performing particularly well because we weren't using particularly deep neural networks. And there was quite a lot of instability in the training. We have a model that we know works and can make classifications. But now what we're interested in is the model actually interpretable? And that's a bit of a tricky one, because what we find is that if we visualize the entire argumentation graph for, say, the CIFAR10 dataset, which the CIFAR10 dataset is a dataset with 10 classes, and we're trying to classify it as, say, one of these animal classes, like a horse or a cat or a frog, or one of the vehicle classes, like a truck, a boat, a car, and so on. What we found is that if we visualize the entire QBAF with this data set, it might be quite overwhelming, and it's difficult for us to fully parse all of the interactions that are happening and which pieces of evidence we're most interested in. But because we have this graph, what we can do is actually generate faithful explanations just by looking at subsets of the graph. So for that same graph that we're looking at before, if we just wanted to figure out why are we classifying this boat as a boat and not classifying it as a truck, we can look at a small explanation of the graph to understand why that's happening. So this explanation shows that all but one of the trucks is irrelevant to the new case. And additionally, we have one image of a boat that's actually taken from above, and that one is also irrelevant to our new case. Whereas all the other images of boats were taken from like a side-on view, which is much more similar to the image that we're trying to classify on the left. What we can also see is that there are no attacks from the trucks to the ships. So if we think about our attacks in terms of the idea of evidence being exceptions to each other, what we can see is that all of the boats are kind of exceptions to being a truck. So boats are, the model has seemed to learn that boats are more exceptional representations than trucks are. And because of these types of interactions, when we compute the semantics, what we find is that the target argument for class 8, which is the boat class, will end up having a greater final strength than the target argument for class 9. And so that explanation gives us a reason for why the boat is predicted as a boat, also why it's not predicted as a truck in this case. So to conclude, I've introduced deep arguing, which is our novel neurosymbolic approach for more interpretable classification. We demonstrated how deep arguing can use explicit argumentative reasoning while still leveraging the flexibility of deep neural networks. And in the future, what we want to do is try and improve our visualizations and interpretation of the model so that we can actually see not only the interactions between the data points, but also what features the deep neural networks were looking at when it crafted those interactions. We also want to look at different ways of doing case-based selection. So rather than just doing k-means clustering, which we do in the input space and isn't really included in the learning process, we want to see is can we actually include case-based selection during learning? So we could do that through object-centric learning using a method called slot attention, or through prototypical part learning as well. Also, what I'm going on to do next is apply this deep arguing model in real-world healthcare data sets. So thank you for listening to my presentation. You can scan the QR code if you want to check out this paper. And please let me know if you have any questions.
Thank you very much, Adam, for your presentation. Very interesting. Okay, now let me check questions from the audience.
I have a couple of questions. Can you hear me?
Yes.
Yes. Yes, Rodrigo, you can go ahead.
So I have a couple of questions. First one is, how do you decide on irrelevance? Like, what's the intuition beside that? It's just it's neither support nor attacks, so it's kind of a zero score, or
So irrelevance is always irrelevance is always a type of an attack. The way we compute irrelevance is as we use the same function that we use to compute attacks for the case space, but we use a negation of that function. So the reason for that is that if, say here, this ship, if it's, let me get the laser pointer, this ship is attacking this truck, right? So what we can think about is that this ship is more exceptional than this truck. When we consider irrelevance, what we want to say is anything that might be more exceptional than this boat should be irrelevant to it. Because we only want to be using the things that are kind of less exceptional or most relevant to that boat. So we use a negation of that.
This notion of exceptional did not come up during the presentation very much. When you explained the dynamic of the model, there was no concept of exceptionality that I could tell. So how is that coming into place?
Yeah, so exceptionality is, I didn't talk about exceptionality in this presentation because it's a bit of a confusing concept when we're looking at things like images. But when you look at tabular data sets, particularly data sets which only include things like binary variables, which is how this entire method originally started, was just looking at binary variables. The idea was that if you have data points which are kind of exceptions to earlier rules, then that would be how you determine what an attack is. The problem with those earlier approaches is that you had to handcraft what you meant by exceptionality, whereas here we're letting the neural network learn what is meant by exceptionality. But because the neural network is learning what that means, it's not as clear-cut that it's strictly a notion of exceptionality. So I talk about it a bit more generally as this notion of just attacks.
So the ultimate signal for this training is the labels, right? This is still a classification task, only you are doing this argumentation on top of it. Not on top, but kind of as a part of the classification.
Exactly, yeah.
So why does arguing help with classification? Why not just use the plain classification model?
Yeah, I mean, it's not so much that it helps strictly with the classification. I mean, we see in the performance.
For interpretability.
Yeah, exactly. The goal is that can we actually interpret the model? So we're trying to imbue explicit reasoning into the model. And in this case, we're doing it through argumentative reasoning.
I see.
Can you hear me?
Yes.
Yeah, we'll have a few questions from the audience if, Rodrigo, you think you're done with your question for now.
I'll let the audience ask more questions. I still have one question that I can add at the end if there's time.
Okay, sounds good. So first question from the audience. By the way, can you hear me okay? I was told that my sound wasn't. Okay, good. Any comparison against K-graph?
K-graph. I'm assuming that's in reference to, is that like K nearest neighbor? We ran experiments comparing performance against K nearest neighbor on the tabular data sets, and we found that it performed quite similarly to the decision trees. The main difference with the explanations generated by things like K nearest neighbor is that it only says which data points are most similar to the one that you're trying to classify, whereas the explanations that we provide also say why not another class. So that's what we get from the argumentative reasoning. And then also, because we're doing this method of end-to-end learning, we can scale to things like imaging data sets and so on. Although I know that there is some work as well in using K-nearest neighbors trained end-to-end with neural networks as well.
Thank you. The next question is, how is the ambiguity between classes 8 and 9 resolved when both obtain similar argumentative strength scores?
Yeah, I mean, so that is actually a problem. But this is a problem that would come up in like neural networks in general, right? Like if you have your output neurons and all of the output neurons end up with a similar logic once you do the classification. So, I mean, we resolve it in the same way that you resolve it with a neural network, which is you just arbitrarily choose. I think typically using the PyTorch implementation, it just chooses whichever class is earlier in the indexing. Yeah, I mean, you hope that during learning, you would very rarely end up in a situation where, you know, more than 2 of the target arguments end up with a similar acceptability score.
Thank you. The next question is, can you elaborate a little further on the glioma case?
Sorry, could you repeat that question?
Yeah, 1 second. Maybe can show the question on the screen. So can you, the question is, can you elaborate a little further on the glioma case?
Okay, yeah. So the glioma dataset, it's a fairly small dataset with the goal of classifying whether certain genes that are provided are, whether the genes represent a high-grade glioma or a low-grade glioma. So these are different types of brain cancers in that dataset. And because it's a fairly small dataset, what we found was that when we ran it on both our deep arguing model and on the gradual ACBR, the deep arguing was able to perform much better. So as I think I said in the talk, it was because it was able to run on gradual ACBR because it doesn't have as many instances as the other data sets. But it performs pretty poorly because in gradual ACBR, there was no real optimizations for preventing cycles. There was an optimization preventing certain pairwise cycles where argument A attacks argument B and B attacks A, but no other optimizations like that. And also, it only used neural networks which were one layer. So as a result, it ran into loads of instabilities. It wouldn't always converge. Sometimes it would run into issues where certain output target arguments weren't connected to the graph. That was why we end up seeing lots of that's why we ended up seeing that with the glioma case here, the performance of that model wasn't very good. And we were able to overcome that issue with deep arguing.
Thank you. The next question is, how are argumentative graphs constructed and used for classification in the MNIST dataset within the deep arguing framework?
Yep. So sorry, my dog just walked in there. The graph is constructed in the exact same way that we would with the CFAR 10 dataset. So unfortunately, I don't have on this laptop any images of that. But essentially, what would happen is that with the MNIST dataset, we're trying to classify whether hand-drawn digits from 0 to 9 are, what digit it actually is. And we would again generate interactions in the same way. So we might see, for example, images that represent the digit 0 would be attacking images that represent the digit 1, for example. And again, we would model all of those interactions for all of our case space. The only difference really between how we do it for CFAR 10 and how we do it for MNIST is that our feature extractor for MNIST is a convolutional neural network. So it's a bit of a smaller model. And the main reason for that is just because MNIST is an easier data set to classify.
Okay, thank you. The next question we have from Discord. How do you handle vanishing and exploding gradients during the fuzzy logic inference?
Yeah, that's a great question. So we ran into loads of issues with exploding gradients and vanishing gradients initially. So one of the things with the fuzzy logic, which I didn't actually, here it is. So I didn't actually talk about it in this talk, but when we do the fuzzy logic, so the minimality condition has to check over our entire case space for which case is the most minimal. And if we applied the min function here over all of the case space, then we would actually run into lots of issues with the gradients. So with the Gödel logic, you run into issues where you're only updating a few parameters. In the gradual ACBR approach, we were using the product fuzzy logic, and there we were running into lots of vanishing gradients because we were multiplying lots of values between 0 and 1 together, which led to lots of small gradients. So what we did here is, instead of actually using min, when we were doing the minimality condition across large case spaces, we used a method called log sum exp, which is essentially a soft approximation of the minimum function. And we found that that leads to better gradient flow because it allows for gradients to flow back to more parameters, not just the one that ends up being minimal.
Okay, thank you. These are all the questions from the audience for now. I have one relatively quick question from myself. Have you tried it on textual data, or like, I believe you have not, but like any reasons or any plans to try it on textual data?
Yeah, no, that's a great question. So we've in the past used a similar method with, well, not in the past actually. I have a master's student currently who's working on a similar method, looking at planning applications for the UK government. And what they're trying to do is extract features using LLMs and then use a similar version of this case-based reasoning to make predictions about whether a planning application would be accepted or rejected. Currently, that approach doesn't do any end-to-end learning. It's a pipeline neurosymbolic approach, but the plan is to then go on to test it using this deep arguing method where we do the learning end-to-end. We've also looked at recently an approach called inference time argumentation. And in that, we're using an LLM to generate arguments for why a claim might be true or false. And we used a similar method of end-to-end learning there, where we trained a large language model to be able to predict base scores, for example. So we've not quite tested deep arguing on text data, but we're almost there.
Okay, thank you. We've got one more question from audience.
I have another question.
Rodrigo, we have one more question from audience.
Okay.
If you don't mind, quickly. So the question is, do you think the use of argumentative graphs in deep arguing adds significant complexity, primarily for performance improvement only?
Yeah, so it will add additional complexity. So because the argument graph because it's represented using adjacency matrix, the representation is n squared compared to the number of cases that you have in your case space. And then additionally, when we compute the minimality condition, because we're comparing every pair of arguments with every other argument when we enforce this condition, that operation is n cubed. So there are some issues with complexity, and it is definitely slower training than with standard neural networks. But because we're able to make the case space smaller using our case-based selection methods, and also because we do things like batch operations, we can actually get faster performance. So it's definitely a trade-off, but it is one that we are considering and have worked to address.
Related from myself, did you by any chance compare the number of parameters in your model versus the deep neural networks that you compared it against?
Yeah, so we didn't do that explicitly. When I picked the models, I used the exact same feature extractor for the deep neural networks. So there it would have been the same number of parameters anyway. And then the only difference really would have been that the parameters in the deep neural network, because it just has one final feed-forward neural network to make the classification, there would have been actually fewer parameters in the deep neural network than compared to in deep arguing. But I don't think the actual difference was not that large, because most of the parameters are within the feature extractor.
Okay, thanks. And these are all questions from the audience, so Rodrigo, you can go ahead with your question if you have any.
Just a not very crucial question, but in the forward step, you say that there you have a step for fitting. Yeah. And I didn't quite capture what that means.
So the fit step is where we actually build the argumentation graph. So we first construct our QBAF. So that's where we do the kind of forward pass of our neural networks in order to compute the edge weights and the base scores for all of our arguments. So the fit step is where we construct the graph, and then the prediction step is where we actually apply the argumentation semantics.
So the graph, the argumentation graph, is built at every pass?
So it's built at every pass, but because we do batching operations in practice, we actually end up not building it for every new case that we do. We end up building it for a batch of new cases.
Okay.
And then once training is done, we can just build it one last time, and then we never have to keep rebuilding it.
Because the word fit kind of gives me the impression of learning, but this is a forward pass, which would be before the backward pass. So that's what was confusing me a bit. But it doesn't do learning; it just builds the graph, right?
Yeah, exactly. I think the word fit there is maybe a bit of a legacy term, because originally, before we were doing end-to-end learning, when we would build the argumentation graph using the symbolic operations only, we considered that to be a fit step, as you would traditionally expect. And so we use the same term here, but yeah, you're right.
All right. Thank you. Very interesting.
Mm-hmm. And since we have a couple more minutes, one last question from mine. Maybe, Adam, if you could show your slide about interpretability again, like this example. So I don't quite understand why you have two kind of threads there. Yeah. Yes. Yes. It has 10 classes. So why don't you have like 10 classes represented here? So is it like in general, like my understanding was if I have 10 classes that potentially all of them may affect interpretability. Isn't it the case?
Yeah, no, exactly. You're 100% right. And this is the full graph with all 10 classes represented. So here at the bottom, we can see these are the 10 classes that we're aiming to predict. These are our default cases. But what we found is that this graph on its own is quite difficult to parse. So it's hard to see what the interactions are that are occurring. So what we can do is just filter to the interactions that we're most interested in when we're generating explanations. So this is just one explanation that we could generate where I've just filtered to the class for ships and the class for trucks. But I could have picked any other types of classes to look at as well to generate explanations from our graph. But you are right, all of the 10 classes do contribute to the prediction that we're making.
Oh, so on the next slide, it's not shown like the whole interpretation. It's like part of the interpretation. Why it's not like a truck, why it's a boat, right?
Exactly, yeah. So here we're just generating one explanation of the many possible explanations we could generate.
Okay, so if I try to understand the whole picture, it should be enough for me to look at 10 of those. Is it correct? Like I mean, asking a question, why it's not a car, why it's not like, I don't know, a bird, like, so if I'd like to get kind of the whole picture, why is it a boat? How many of those explanations do I need to generate?
Right, yeah, I see. Yeah, so you could look at like 10 of these explanations to see why it's one class over another. The thing is as well is that because we have sort of more complex interactions than that, you could also look at, rather than 2 classes at a time, you could look at 3 classes at a time, for example. So you could say, okay, why is it a boat, but not a truck and not a car? And look at how those interactions occur as well. Because there'll be interactions between the trucks and the cars as well, even though you're only interested into why it's a ship. So it really depends on what explanations you're kind of most interested in, rather than looking at kind of a complete picture. Because if you want to see the complete picture, that's kind of just this graph here.
I see. Okay, and we are at time. So thank you very much, Adam, again, for your presentation today. Very interesting. And yes, see you all in a week. Yeah, thank you. Bye.
Thank you very much. Bye.
Thank you.